Hello, welcome to everyone in this video. This is lecture number 17 on solid state physics. Today we want to discuss about the elementary band theory. In this video we want to cover up this portion, that is the Kronig Penny model, band gap, effective mass and effective mass tensor, conductor, semiconductor, p-type, n-type, insulator, then conductivity of semiconductor, mobility, then Hall effect, and then measurement of conductivity four-form method and Hall coefficient. All the parts on the elementary band theory will be covered up in a single video. You can see this is the syllabus of this syllabus. This part 1, crystal structure, elementary lattice dynamics, magnetic properties of matter, dielectric properties of materials, already covered. In the last section we discussed the Drouet's theory, and in this portion we want to cover up this part 6, that is the elementary band theory. So let's start. First things you know, that is for a single atom, for hydrogen atom, the energy levels are like that. Potential barrier is such that the energy levels will be like that when this is a single hydrogen atom. But when they are arranged in a periodic manner, if this arrangement in one dimensional, then the energy levels will be like that, and after a certain height this energy levels coincides and making a band. Okay, so band is nothing but the collection of energy levels. So very much a large number of energy levels makes the energy band. So the potential is periodic. That means after a certain distance, the potential repeat itself. So V of x plus a, there is length of a, which is the length of periodicity. That means after length a, this potential will be the same as at point x. So the first one dimension Schrodinger wave equation, you know, this is the one dimension Schrodinger wave equation, and its solution can be taken as this one, and this is the this function also periodic function. This is known as Bloch function. So this is actually Bloch theorem. Bloch theorem says that is the total wave function is this periodic part and e to the power plus minus ikx. So this is the Bloch theorem. This can be derived as that. You can see this is the one dimensional Schrodinger wave equation. Since the potential is periodic, so you can take these two independent solution, f of x and g of x. So psi of x is the linear combination of these two independent solution. So psi of x plus a is nothing but x is replaced by x plus a, and this f of x plus a is the combination of these two linear independent solution also. So f of x plus a equal to alpha 1 f of x plus alpha 2 g of x, and g of x plus a is nothing but beta 1 f of x plus beta 2 g of x. Now if you substitute this f of x plus a and g of x plus a in equation number 2, you can put this one and separate out f of x and g of x, this taken as qa and this taken as qb. So finally you will obtain q psi of x. So psi of x plus a is nothing but q psi of x, where you take this qa equals to this one, this portion take as q into a and this portion taken as q into b. So take this one and separate out as the constant a and b. So for non-trivial solution, the determinant will be equal to 0. So this multiplied with this one and this, finally you will obtain this equation, right? So to find the value of q, actually you can see here we obtain this relation. The relation is like that. You obtain this relation, that is this psi x plus a is nothing but q into psi of x. So you just wants to find out the value of q, then you will be obtain this Bloch theorem easily. So to find the value of g, you just remember that is f of x and g of x, the independent solution of psi of x. So f of x and g of x must be satisfy the equation of psi of x, that is the Schrodinger equation. So these both f of x and g of x satisfy the independent solution of psi of x, satisfy the Schrodinger equation. So put this value in the Schrodinger equation, and if you multiply this equation number 5 by g of x and this equation number 6 by f of x and subtract them, you will be finally obtain in the right hand side is 0, because these two are cancelled out. So this is nothing but ddx of this one, and you know very well this is the one scheme. from the mathematical physics, you know, second order differential equation solution in mathematical methods, you very well about the Wronskian method. So this is nothing but the Wronskian, and you know the Wronskian have a property that is w x plus a equal to w. So you just follow up this property, put x replaced by x plus a, and d x of f of just put this value of g of x plus a and f of x plus a. Here you can see that is the f of x plus a, and this is g of x plus a. Put these two value and rearranging, then after you will be finally obtain this relation. Okay, so I think you can do this calculation. If there is any doubt, you must comment in the comment box. So after getting this relation, you will be obtained that this one. So using the properties of the Wronskian, you can say this value is the 1. So if you put this value is 1 in the equation number 4, that is the equation number 4 we already obtained, that is this value is 1. So if you put this value is 1, you will be get the second order quadratic equation, and you take this as gamma. So finally you obtain this relation, these values. So if gamma is less than 4, that is the complex number, so they are complex conjugate solution, this one. So you will be obtain this equation because the q value is written here. Psi of x plus a is nothing but q psi of x. So put this value of q. But when this gamma square greater than 4, then there is just real. So reals means there is no wave function, because you know for wave function there must be a complex, because in complex can be written as in the summation of sine and cos. So these are the forbidden. Okay, and you can see these energy levels are allowed because this wave function can be for the electron. So from that starting point, from that point you can say that is the electron have some forbidden region, electron have the some allowed region. So there is a band structure in presence of forbidden gap, that is the band gap is already obtained, or that is discussed here or concluded here. So this is the starting point of the theory of solid, band theory of solid, because here you will be get these bands concept, that is the some allowed state and some forbidden state. After that, the important model is the Kronig Penny model, which used to understand the structure of a material or the lattice structure. That's take actually in the previous balls this was taken as the periodic potential as a this. Okay, and this periodic potential changed into by Kronig Penny by the square barrier. So this is the modification by the Kronig Penny from the board. Okay, so this potential can be equation as like that from the quantum mechanics. You can use this Schrodinger equation, this one for that region and this one for that region, where alpha and beta is like that. So their solution of these two equation will be like that, and you psi of this one from Boss theory. So you k equal to like that. So put this derivative and second derivative, you will be get this relation, and from equation 3 and 4, that is you just put this equation 3 and 4, this relation will be after this equation for 1 and 2. Okay, I think you can do this calculation. If there is any doubt, you must comment in the comment box, or you can contact with me. So just using this relation in 3 and 4, you will be obtain this to 5 and 6, and their solution, differential equation solution will be like that, where a b c are the arbitrary constant, and this can be find out by the boundary condition, that is the continuous at x equal to 0, that is this is continuous and the derivative also continuous, and periodicity means at x equal to a and x equal to minus b are the same function, so periodically these two are equal. So using these four condition, you will be get these four relation. Okay, very simple. For just put this condition, you can easily find out these four relation. And for non-zero solution, the coefficient of these four constant, that is the A, B, C, and D, the coefficient must be satisfy this determinant, which is equal to 0. So use this determinant, you can easily find out this expression. Okay. So this is a long calculation. You know to find how to find the value of determinant. Just taking this one and this determinant, this one and this determinant with the minus plus minus plus minus and so on, and finally after the long process you will be obtain this relation. Okay, if anyone wants to do, you can just check, but at your exam purpose I think you just remember this expression finally. Okay, so to obtain more convenient equation, Kronig Penny take this as a delta function. That means b tends to 0. B tends to 0 means you can see this potential well, that is this b tends to 0 means just like a delta function. Okay, actually this will be delta function because this dimension of the nucleus is very much lower in compared to the radius of the electron cloud. So this will be physical, not in physical, this is a physical concept. Okay, so you can take this b tends to 0, so v0 b equals to finite finally. So b tends to 0 means sin beta b tends to beta b and cos beta b tends to 1, and beta square plus alpha square, beta is high, so this will becomes beta square, finally will beta by 12. So you put this expression, and after the calculation or putting the value of beta square and alpha will be obtained this expression, and this is the well-known equation for conic Penny model. Okay, here this is taken as p, and p has a significant meaning. If you put this plot this graph with respect to a, will be these things, and you can see there these are the allowed region. Okay, you can see this is the forbidden region and the shadow regions are the allowed regions, because this value will be from -1 to +1. So up to this one, this is valid, and these are the forbidden region. So for cos k plus minus 1, so we will be obtain this range. So what are the range where this is the continuous, actually mathematically obtained here, and these are known as the Boolean zones. Boolean zones. Significance of p, you can see this is the p, and this dimension, if you want to find out the p, because this is a dimensionless sign of alpha a means alpha a is dimensionless. So this is also dimensionless, and this is also dimensionless. So finally p must be dimensionless. And if p tends to infinity, this is a strongly bound, and p tends to 0, this means loosely bound. Okay, for p tends to infinity, if you take this is infinity, so this must be equals to 0, finally we obtain this expression, energy expression, and you know this is the discrete energy levels for a quantum wave. So this becomes a energy level. So that's mean in this graph this will be the just line, not a band, it's make a line energy levels. And if p tends to 0, so this is broadened out, and this becomes like that. So this is a continuous spectrum. There is no band or the forbidden gap. There is no band or the forbidden gap. You will be finally obtain this uh, continuous spectrum, that is the continuous energy spectrum, like a free particle. Okay, so p tends to infinity means the tight bond, and p tends to 0 means free particle. And if you wants to find out the Boolean zone, we just before we obtain these k values, and this is the first Boolean zone, this is the second Boolean zone. In the graphical representation, you can see this is the free particle, and if you consider there is a allowed state and forbidden state, so these are the forbidden gap, and after this forbidden gap, this expression, this curve is written here, and these two combination after this portion and this portion, just flip in this case. Just if you flip these two curve, you will be obtain this curve. Okay, and after flipping this curve in 2 times, you will be obtain this curve. So all the Boolean zones are reduced in a single state. The single region is known as the reduced zone scheme, right? So this is the extended zone scheme, and this is the reduced zone scheme. So you just think about the Boolean zone for a one dimension, and in 3 dimension you will be already know about the Boolean zone in the previous solid state physics lectures. So I just say that is this portion and this portion just flip, you will be obtain this card. Okay, this and this portion is flip two times, you will be obtained. So this all loss is reduced in a single Rayleigh zone. So that's why this is called reduced zone scheme. Okay, and from the figure you will be, according to the Bragg's law, you will be obtain this relation. And for normal collision, when the incident is normal, the theta is 90 degrees, so you will be obtain this relation. Okay, so you can say this, that is the electron behaves like a X-ray photon. Okay, so you wants to find out the number of possible wave number in a band. So if you wants to find out the number of possible wave function in this band is like that, that is a consider a finite crystal of length L, and determine the number of possible wave number of this band. The number of primitive cell will be n. So periodic is expression this thing. So from the Gauss theorem, you know this relation, and putting this value, you will be obtain this expression. So the value of k will like that. So for the number in the decay region is like that, u by 2 pi, this one. So total n equals to the total integration. So this gives you the final value of total n. So for each state, two electrons are here, so we need to multiply it with the 2. So finally you will be get this resistance 2n. Okay, there is a 2n number of electron in a band. Now you need to know about the concept of effective mass and the effective mass tensor. So effective mass means when you know about the energy. Suppose the energy is nothing but for is the work done is converted into energy. So work done is nothing but the force into displacement. Force is minus E into E. This currently is nothing but the electric field, and this is the velocity into time, that is the distance. So velocity is the group velocity is d omega by dk, and you know E equal to h cross omega, so omega equal to E by h cross. So finally you will be equal to like that. Put this value of V here. So this one again, the E is a function of k, so dE by dk is like that. So if you compare these two things, you will be obtain dk by dt equals to this one, and the acceleration equal to dv by dt. Put this value of a b with this one. So finally you will obtain this one, and dk by dt you will already obtain that minus E epsilon by h cross. So this, then the effective mass is nothing but force per acceleration. Force is minus e, and this is acceleration, so this is the effective mass. Actually, within this material or the periodic potential region of a material, you get that is the changed mass. This mass is not the actual mass or the free mass of the electron. This must be this mass actually changed, and this changed mass is not actually effective mass, which mass actually gives you the information in the within the material. Okay. So this is the expression of effective mass, like that. But in case of the free, that is the no potential, so E equal to this one, so d by dk equal to like that. So if you put this value, you will be get the effective mass is the rest mass cell. And in the tensor form, this effective mass can be written as like that. So there is a 9 component present here. So this is a notation where the effective mass can be expressed in a tensor form. Next thing is the conductor, semiconductor and insulator. According to the conductivity, the conductor has a much conductivity more than the semiconductor, and then the no conductivity of the insulator. According to the band structure, the band gap between the valence band and conduction band in case of insulator is very high. In case of semiconductor, this is low, and in case of conductor, they are superimposed or overlapped. Okay. In semiconductor, there is two type of semiconductor: intrinsic and extrinsic. Intrinsic means there is no doping. Extrinsic means there is doping. Extrinsic semiconductor further to classified N type, P type. N type means the pentavalent, that is the number of electron in the conduction means larger, that is the majority carrier of this n type is electron and majority carrier of p type is hole. And this is the conductor whose conductivity is much higher. Okay. Next important thing is conductivity of semiconductor and the mobility. Mobility is defined as that the drift velocity per unit electric field after electric field. So if there is a semiconductor and if you apply the electric field by placing the voltage source, by placing a voltage source, you apply the electric field. So electric field per the drift velocity is originated by per unit electric field, that is if you apply unit electric field, what are the drift velocity attained is known as the mobility. And resistivity is nothing but the resistance offered by this material per flow per unit length per unit cross section. That is, you know this relation of r equals to rho l by a, you know this relation very well, r equals to rho l by a. So rho is nothing but r a by l. So if you put a equals to 1, l equals to 1, so rho equals to r. So this is the definition of this resistivity, that is the resistance offered by a q. You can say this a is 1, l is 1, that is the q of unit length. So this is the resistivity, and inverse of the resistivity is known as conductivity. Resistivity means a force exerted and conductivity is flow of the current. The reciprocal of the resistivity is conductivity. Within a semiconductor, total current is due to a hole and electron, because there is a two types of carrier in the semiconductor. One is hole, another is electron. So total current will be contribution of the electron and hole. In case of hole, you know the current expression is nothing but current equals to charge per time. So charge is number density into volume, that is the number into electronic charge. So this is the total charge by time, and L by T is V. So A N E V is the current expression. So the N is the density. Here is the considered the hole. So this is the hole density, and this is the velocity of hole, deep velocity of hole. Similar for the electron, this is the electron density, and this is for the velocity of drift velocity of the electron. So their summation will gives you this relation. And the resistance is nothing but voltage per current, so V by I. Put this value of I, and the resistivity is like that, R equal to rho L by A. So resistivity will be this one. Okay, A is cancelled out, and E by E equals to V by L. So V by L is replaced E. So if you just common this E cancel out, finally so conductivity is the reciprocal of this one. So this is the conductivity of the semiconductor in terms of the hole density, hole mobility, electron density, electron mobility. This is the hole density, this is the hole mobility, this is electron density, this is electron mobility. This is the total conductivity of the semiconductor. You just think about two things, that is the mobility of the electron is much higher, is higher than the mobility of hole. This is the experimental result, and from that you will be obtain those two experimental result, that is the temperature effect on the semiconductor. You know, in case of intrinsic semiconductor, if you increase the temperature, then carrier number will be increased, that is the concentration of the carrier for electron and hole both are increased. The increased carrier concentration result in a higher conductivity. So in case of intrinsic semiconductor, if you increase the temperature, then the conductivity will be increased. But in case of extrinsic semiconductor, there is large number of carrier concentration already present. If you increase the temperature, then the mobility reduced, and due to mobility reduction, the conductivity reduced. So in intrinsic semiconductor, with increasing temperature, conductivity is higher, but in case of the extrinsic semiconductor, with increasing temperature, conductivity reduced. These are the two results obtained. And another important thing is that value of mobility is for silicon at electron for electron mobility, and this is for hole mobility, and this one, etc. And this mobility is inversely related to temperature, just say here, and the inversely proportional to the doping concentration. and with the variation of E will be like that. For low value this is constant, this is root E, and this is 1 by E variation. This is important for your exam purpose in this term. Now comes into the point the Hall effect. In case of the today's theory, we already discussed about the Hall effect in the metal, because in metal there is only one carrier, that is electron, so Hall effect is present due to only electron. But in case of the semiconductor, there are both types of carrier, electron and hole. That's why there is some modification in the Hall effect. Hall effect, when the current flow in presence of perpendicular magnetic field, there is a Lorentz force. This Lorentz force is nothing but Q V cross B. When this Lorentz force is applied, these charge are moving towards perpendicular both field and current. So this charge accumulated here. After a certain accumulation of this charge, they cannot fold, because this accumulation of charge result in electric field, and this electric field gives you the force opposite to this charge particle. That's why after a certain value of the accumulation of charge, they cannot further accumulate it, because this arrangement or accumulated charge produce the electric field which opposed to come the further accumulation of the charges. So this electric field and the electric field force and the magnetic field force are equal at equilibrium, so you will obtain this Hall field, and from Hall field you will be obtain the Hall voltage. That is, if you apply a voltmeter, you will be obtain this amount of voltage across perpendicular to the sheet. Now the drift velocity is nothing but length by time, and this current equals to q by t, so t equal to q by I, and the resistivity charge density is q by v, so v is lwd. 3 are the dimension of this sheet, so L equal to q by rho wd. So put this value of L and t, will be obtained Vd, that is the drift velocity is I by rho wd. So the Hall voltage is replaced here. Just put this value of Vd, you will be obtain this expression. Okay. So we want to change this expression, because we just find out because we cannot find the drift velocity directly from this experiment. So from experiment we will be obtain this expression. So using this formula you can find out the Hall voltage by the experiment and the corresponding Hall field. And Hall coefficient is nothing but, because the Hall voltage arises due to field and the current, so they are ratio. That means how much Hall field arises due to current density and the magnetic field. Okay, so this is the Hall coefficient. So H is nothing but Vh by D, and this J put this value of Vh Hall voltage, you will be obtain this expression. So finally you will be get Rh equal to 1 by rho. Okay, uh, and 1 by any, or further another expression is like that. So I think you do this calculation. If there is any doubt, you must comment in the comment. So you will be get the Hall coefficient, and this can be find out from this experimental result. And from the Hall coefficient you will be obtain some important results. I just want to say about the important result is that application of the Hall effect, that is from this Hall coefficient you will be get the type of the carrier, whether this electron or hole or both. You will be get the density, charge density, you will be get the carrier concentration, you will be get p type or n type information. You can be determine the magnetic field, which actually used in Gauss meter, where the magnetic field can determine, and you can get the velocity, conductivity, mobility. So these are the important application of the Hall effect. And there this actually previous year question where says that is the Hall coefficient in terms of in terms of electron and hole both. So if you take this consideration of the hole and electron both, you will be get this current density and this is conductivity, and the corresponding velocity equal to distance by time, that is the half force into mass, effective mass, tau square, half it is square formula. So obtain this expression velocity, and this holes and electron have this type of force, Lorentz force exerted, so corresponding velocity will be like that. And if you consider these two things, finally you will obtain this expression, that is the Hall coefficient, and this is for 0 for intrinsic semiconductor, this is for positive for p type semiconductor, this is negative for n type semiconductor. So all this information obtained from this expression. So I think you can do this calculation very well. If there is any doubt, you must comment. Next important thing is the measurement of conductivity using 4-4 method. Before that, you know, that is the two probe method, where there is voltage source. Actually, this voltage measured from the others 2 point, but in two probe method, this voltage also measured from these 2 point. This is the basic difference. And what happen in case of two probe method, this junction effect, at the junction there is a variation of the fields, and that's why the potential actually different, because at that point this potential measure the external source. Actually the current flow within the material cannot determine in the two probe method. That's why you need to know, you need to take the 4 probe to determine the actual resistivity of this material. Clear? When we apply the voltage source into these two port, you will be get the influence of the value of the external voltage source. But when you apply the another 2 point to measure the voltage, there is actually voltage which is due to the current flow within the material. So you will be get the actual resistivity of the material when you use the 4 port. So just do this mathematical expression, that is R equal to L by A. So this small region, the resistance will be rho dx by A. Dx is the distance, small distance here. So the integration, you can see that is the voltage is measured at point S to 2S. So that's why integration limit is S to 2S. And the area actually 2 pi x square. Why? When this thickness is very large, these fields line are spherical, and this is hemisphere. That means its upper side is not conducted or not included. So this hemisphere area is 2 pi x square. So integrating this one, and finally this expression, and you know v equals to r equals to v by I. Why use 2? Because due to these two port there is one current, there is another current, that's why this 2I. So comparing, you will be get the expression of conductivity. So using this 4-4 method, you can easily find out the conductivity. Using this relation, you will be obtain the value of I from this ammeter and voltage from through. So using this I and V, you will be obtain this conductivity. The condition is that the thickness of the material is much higher, but in case of thickness is very low, then what happen, you just see this, this can be taken as a spherical surface. This cannot form because the thickness is very large, so this form a circular circle, circular part. Okay, so the area will be changed, and this will area will be 2 pi x into t, 2 pi x into t. So if you integrating, you will be obtain this expression, and from the r equal to v by 2I, you will be get the conductivity relation. So you just know about the thickness of the material. If the thickness is much higher, then use this formula. When thickness is very low, you use this formula. Okay, to determine the conductivity or resistivity of the material. So 4-4 method is best method compared to the, is better method compared to the 2-4 method, because of the measuring the voltage of the system. Okay. And the last important part is the Van der Pau method. Van der Pau method actually helps us to determine the conductivity as well as the Hall effect. So this is a sample. This is the one sample which is can be used in both experiment to obtain various parameter of this material. So electrical property of this material can be characteristics by the Van der Pau method. So this is a very important method to know about the characteristic, electrical characteristics of a thin structure or nanomaterial structure, right? So just think about this. This structure will be like that. This is the power flip structure. The sample structure will be like that. You can make this type of sample using marks. You know, in the nanomaterial synthesis process, you can synthesize these types of semiconductor or thin film very easily. This is the most preferred structure. Otherwise, you can make this square structure acceptable, but this is not acceptable. Okay. So you just taking this to is current source and this is voltage measured, and there is current source, this is voltage measured. So using these four combination you will be obtain 8 resistance taking the average, and after taking average you will be get the resistivity using this relation because of thin film. Okay. And importantly, using this effect, you can flow opposite current and you will be get the hall voltage here. So using this sample you can also measure the hall coefficient, and after measuring the hall coefficient you will be get mobility, drift velocity, carrier concentration, type of the semiconductor, and carrier concentration, etc. So all these things can be measured from this type of sample. So this van der Plas method is the very important. So I think clear. This is your homework. You do this solution. This is actually the previous year question, and the solution of this previous year question are given in the another playlist for the solution of BSc question paper. And this is another question. You must solve this question yourself. This is all about me. This is my contact detail. You can connect with this Telegram channel. And this is my YouTube channel details. Go to this channel. We get different related videos on mathematics. Like this session if you learn something from this session. Share this video to your friends. Either he or she also get benefit from this video. Subscribe this channel if you need this channel. Those already subscribed. Thanks for subscribing. Click the bell icon to get notification of upcoming videos. So take care. We'll meet in the next video as soon as possible. Thank you.